Hey, I'm Sean Rager, and this is my Lab 1 for Georgia Tech Physics 2 about the charge tapes. So, starting with our experimental observations, we've seen pulling one strip of tape away from another causes that strip to be positively charged. We tested this by seeing how it interacted with a negatively charged pen, and they were attracted, so we proved this in the lab. But can we use physics principles to calculate the exact magnitude of this positive charge? We can, using this experimental setup, which one tape approaches another tape that's suspended, and it causes this upper tape to hover, and it's motionless, and it's just standing there with no other materials attached to that middle portion, just motionless in the air. So we can apply two physics principles, mainly the gravitational force, which is affecting that upper tape, which is mass times gravitational acceleration, as well as the electrical force from the lower tape that is acting upwards on that upper tape. And that's force is equal to K times both the charges represented by Q over the distance between the two tapes, R squared. And here's the data we gathered in the lab. The tape length has a length of 0.2 meters, the mass 0.0002 kilograms, the distance between the two tapes 0.003 meters, and the width of the tape being 0.019 meters. And on the right, we applied our physics principles to the tape, modeling it as a point charge, and we see the electrical force acting up and the gravitational force down, and these vectors are equal length to show that they are equal in magnitude. Net forces equal 0, which is why the tape is motionless. Repeat, the tape is motionless, so we can set these two forces equal to each other in our calculations, and we're going to start with our hand calculations. The force of gravity is equal to mass times g, g being the gravitational constant, 9.81, and we get that our gravitational force is 0.001962 newtons. We set this equal to our electrical force, and we are assuming for the purposes of this experiment that each U-tape has an equal charge because they were charged in about the same fashion. So Q squared is a variable in the FQ equation along with K, and they're both over R squared. Solving for Q isolated on one side gets us that Q is equal to 1.4 times 10 to the negative 9 coulombs. And here are glow script calculations, which produce the exact same value for our charge, 1.4 times 10 to the negative 9th. And we also see our vectors modeling our electrical force of both tapes modeled as point charges on each other, as well as the gravitational force on that upper charge. And again, we see that they are equal in length and therefore magnitude. This is a challenge problem from the lab, calculating the fraction of atoms that gave up electrons. To do that, we calculated the area of the tape, length times width, as well as the area of an atom, actually, that was given in the lab instructions. And we divided the area of the tape by the area of electrons, or area of atoms, to get us the number of atoms if they were perfectly arranged in a rectangular lattice. And then we took the charge that we calculated from the last part and divided it by the charge of a single electron to get the number of electrons that were given up to create this charge. And we create a fraction with the electrons as the numerator and the atoms as the denominator. Two other assumptions we made in this experiment was treating the tape as a point charge, as we said earlier, and assuming that each U-tape had about the same amount of charge. We did not have to assume that air resistance was neglected, as there is no main moving object in this experiment. Two more questions that we went over as part of the lab report. If the electrons had a positive charge and protons had a negative charge, this would not change a whole lot. This would change the notation and the way physics is used in our vocab, but as like charges still repel and same charges attract, even if we flip-flop the definitions, we'd still see the same relationships between charged and neutral objects. And finally, it's important to handle the charged tapes as little as possible, because whenever a charged object comes into contact with another object, the electrons will flow to the object with a more positive charge, therefore reducing the overall charge, making the whole system approach neutral charge, so the tape would lose its charge the more it interacts with other objects. And this completes the charged tape labs, showing how we can solve for the precise electrical charge of an object just by using a motionless state and a known force.